I want to thank you all for coming to our first lecture of a series of radio astronomy talks that we've organized in the last few years. This series is funded by Phyllis and George Halburn. We call them now Phyllis and George Halburn Radio Astronomy Lecture Series. And we have one lecture per quarter. We're really delighted to have our speaker and welcome Tony Beasley from National Radio Astronomy Observatory. Tony is a director of the observatory and he's been director since 2012, I believe. Yeah. And his background is that he did his bachelor's degree in physics at the University of Sydney, or Sydney University, that's what you call it there, right? Yeah. And then he stayed there and he did his PhD in astronomy, physics, astrophysics in astronomy. It's a part of a physics department, I believe. And he's had a distinguished career. After he left University of Sydney, he came to National Radio Astronomy Observatory, and he was a postdoc fellow there. And then he started getting into the managerial aspect of the observatory, and not only building a telescope there at the observatory, but also he became a deputy director of the observatory, and then he moved up the assistant director. And then eventually in 2000, his focus was mainly on the design, construction, and operation and management of major research facilities in astronomy. And one was CARMA, which is was a big array of radio telescope that he was the project manager for a number of years. And then CARMA is no longer really operating, and then it got replaced by ALMA. ALMA is the biggest radio observatory that we have on the planet, and it's in Chile, and he became the project manager there. And eventually he was asked to become a director of the observatory. He's one of the youngest member directors at National Radio Astronomy Observatory. Tony has also pursued other interests. In 2008, he became Chief Operations Officer and Project Manager of the National Ecological Observatory Network, called NEON, a continental scale observatory designed to provide scientists with 30 years of ecological data on the impacts of climate change and invasive species on natural resources and biodiversity. But today he's not going to talk about this other sort of interest that he has.
That was my green period.
Green period. But today he's going to talk about his other interest, and that's radio astronomy. So he's going to talk about new radio astronomy science frontiers in the 2020s. Okay, take it away.
Thank you. And thanks for the invite. Can we make this slightly darker up the front here? Is that possible? Yeah. Is it one of those? Is that one? Oh no. Okay. That's good. Yeah, that'll be fine. Okay. Well, thank you. Thanks to Farhad for inviting me, and I certainly appreciate the opportunity to come and talk to you about some of these topics. Today, I'm going to talk about, give you kind of a quick history of radio astronomy. Talk about kind of where the field is now, and then explore some of the options for the next decade. So let's kind of start at the beginning. I mean, why do we do astronomy? There are kind of four main reasons that I've always resonated with. It's a cultural exercise. We like to sort of understand our place in the universe. By looking in the universe, we can see places where the temperature and the density and the magnetic fields and so on are stronger or different to what we can produce here on Earth. So it's kind of a cosmic laboratory for physics. You can do experiments we can't do here on Earth. Along the way, to do these sorts of observations, you tend to develop techniques and technology which can spill over into society and actually benefit all of us. And then maybe most importantly, not everyone can become an astronomer. But along the way, astronomy is a great way of getting people interested in mathematics and science, in in physics, etc. And so the role that we play in terms of science, technology, engineering, art, and mathematics, getting people involved in these topics is very important. Now, historically, we gathered information about the sky, celestial information, from meteorites. Meteorites ramming the Earth and killing dinosaurs as a form of information. Electromagnetic radiation, obviously we could see the stars. In the 19th century, we started to do astrophysics and understand what the light meant. Particle physics, cosmic rays, we've known about for about 100 years or so. And in the past year, we've added something to that, which is gravitational astronomy. Gravitational waves can be detected. So as we look across the electromagnetic spectrum, all the way up to gamma rays and down to radio and TV, this is very familiar. This is a physics school. You understand this. But importantly, different physical properties, temperature, pressure, structure, magnetic field, lead to different types of electromagnetic emission. And in particular, many atoms and molecules emit at unique radio frequencies. So, you could derive that from first principles if you started with Maxwell's equations. In this talk, I'm going to talk about three key epochs of radio astronomy. There was sort of the early era of radio astronomy where it was about techniques. People kind of figured out how they could do some stuff, and they figured out better and better how to do that stuff. Then it became about technology. Once we sort of understood how it all worked, what can we actually build? And then there's sort of this more modern epoch where we sort of have become a little less focused on these two and actually thought about how does radio astronomy play in a larger environment. So if we go back to the late 19th century, people began to understand how Maxwell's equations were derived, and people started to understand how you could produce electromagnetic fields. So radio technology came to the fore. And it was interesting at the time that this was all done, so say the 1880s and 1890s, people did kind of think about whether or not this was another way you could learn about the sky. And so there were some early observations done trying to do radio observations, and in particular to detect the sun. And then there were two equations done, so never believe the theorists. Planck estimated that the radio emission from the sun would be very small, and it kind of is at some level. Also, there was a calculation done looking at the optical thickness of the ionosphere. And based on these two calculations and the failure of just a few observations, everybody walked away from this entire field for 30 years. And in fact, as we know today, that was actually not correct. So there was no attempt for about 30 years. Now, by the time you get to the 1930s, it was possible to make transatlantic radio phone calls. And people realized in those phone calls that there were sources of noise that could not be explained. And so there was a Bell Labs engineer called Carl Jansky kind of put on this problem. What's going on there? There he is. That's him looking very stoic in 1933. So he built this antenna at 150 megahertz observing frequency, and you can see it kind of rotates on this track. And he did this so that he could actually look to see where these different sources of noise in these radio phone calls were coming from. And so what actually happened through a careful process was he realized that the noise was coming from nearby thunderstorms, distant thunderstorms, but then there was this faint, steady hiss. And through a series of observations, he realized that actually that radio emission was coming from the plane of the galaxy. It was coming from the Milky Way. And so that was the discovery, in some sense, of radio astronomy in 1933. So there was a big announcement about this, and Jansky wanted to do more, but his employer didn't allow him to do it. So he actually neatly ends this story. Despite the fact we put his name on nearly everything, he never did another thing in radio astronomy. So the person who did move forward was a guy called Grote-Reber. And he built the first dishes which kind of look like radio dishes we have today. And he drove them around the sky and he started to do measurements. So there's a picture of him in front of his equipment, and he made this sort of first map of the sky at radio wavelengths. So interestingly, this first map, which he derived from sort of driving his dish around the sky, has three scientific observations in it, three new detections. First of all, there's this non-thermal galactic radiation, which no one particularly understood. Secondly, that we can see that it's centered on a thing here, which is the galactic center, which again was, I think we understood there was a center to the galaxy, but it was not measured this way. And then the third thing is that there are some bright sources up here, which are supernova remnants. This is actually a radio galaxy, and this one's the supernova remnant. So with the very first observation, he kind of realized that maybe there was something to this radio astronomy caper. World War II comes along, and there's suddenly a huge amount of investment that goes into radio astronomy, radar and sensitive receiving equipment. And it was actually during the war that someone actually first detected the sun at radio wavelengths, because these coastal installations detected that there were attacks coming at dawn every day. And so people kind of realized what was actually going on, and they wrote it up, but it was not released until after the war. Now, after the war, there were certain countries that had put a lot of investment into this, and they decided to move all of that investment over into science. And so Australia, UK, the Netherlands in particular, moved all of this expertise over into radio astronomy. So the fact that an Australian is talking to you today as the head of a radio astronomy organization is a weird, distant product of World War II in an odd way. We do a lot of this, and there are a lot of Dutch involved and Brits and so on. So there are lots of installations, like coastal installations, that look like this. And then people started looking towards the sky. They started building these large dish antennas with the receiver up here and looking at the sky at radio wavelengths as it kind of rolled over. So this was sort of the late 40s and so on. It was around that time that people realized that they actually could start to build larger dishes. And so that was what we could do in radio astronomy about 70 years ago. We could build large single dishes. And the bottom line was, at this point in history, steel was much cheaper than silicon. Right? I could afford to build a big telescope, but I could only put 1 pixel into the receiving element because the transistors and all of that was still incredibly expensive. And so we were still being driven in some sense by technology here. But there were a lot of telescopes built. This is the Caltech Owens Valley 40 meter. It was the first of what was supposed to be a group of 8 telescopes which were going to be built in California. This is the Parkes telescope, which was built in Australia. This is the Arecibo telescope. So as you build bigger and bigger telescopes to collect more radiation and do more sensitive observations, you get to a point where you actually can't build something that will hold up under its own weight. And so this was an approach using this sort of topology here, where you have these limestone depressions, and you actually put a dish into that. And then you have a more complex system up here to sort of drive, the radiation comes in and bounces up this way, or you drive this over here and it comes this way. So this is 300 meters in diameter. So it's a substantial thing. It actually didn't do so well with the hurricane going over it recently, but it is observing again. Now, we still build these single dish telescopes. There are still science applications for single dish telescopes where you need collecting area. These days we tend to be able to put more electronics on them, so we have more pixels on the camera, if you think of it that way. This is a telescope at the South Pole that was worked on by someone here. This is the Green Bank telescope in West Virginia. So this is, I would have said that this was the state of the art in terms of building a large single dish telescope. This is 100 meters across. This is the size of a football field here. And this thing here weighs 16 million pounds. And so it's actually, it's an offset reflector, which means the radiation comes down and bounces up to the receiving elements up here. Now this telescope is still observing at frequencies which are like your cell phone frequency, frankly, or a few times your cell phone frequency. And so this area, which is actually, I could pretend it was the hills here. It's actually about 90 miles in every direction from the telescope. This is in a radio quiet zone in West Virginia, because that's one of the problems with single dish telescopes. They're very susceptible to interference. So this is the largest steerable telescope at the moment, although the Chinese are about to start building 3 telescopes, 2 or 3 telescopes which are 10 to 20 meters bigger than this, because they're doing a lot of stuff and they have a lot of money. So, but the largest thing built recently, this is FAST. This is the 500 meter aperture spherical telescope. So it is difficult to give you a sense of scale here. This is also limestone depression. This is in sort of southern China, sort of in the middle at the bottom. And you see these large towers around here, and then you see this dish. So this is 500 meters across. And in fact, the way this dish works is that there are actuators that sit under the dish that pull the dish to form a parabola in the direction that they want to observe. And interestingly, the size of the dish they pull is the same size as Arecibo. They pull a 300 meter dish in the middle of a 500 meter dish. So just to give you some sense of scale, if you go down onto the walkway here and take a photo of the bottom of it, it kind of looks like that. And then you see this little thing in the middle here, if I blow that up for you, there are two people standing there. So it's big. It's like 440 VLA dishes. It is a really incredible amount of collecting area. But again, it has sort of the single dish properties. It has resolution because it's quite large, so it can observe a sort of a fine point on the sky, but it's pretty much 1 pixel. And that was kind of where the field of radio astronomy got to in the 50s and 60s. We could build large single dishes, but we're getting kind of 1 pixel on the sky. So, I don't know that I need to go through this in detail. Typically the dish reflects up to a subreflector. The subreflector often then directs the radiation down into some kind of feed system, and then sitting below those we have electronic feeds. So if I took a chainsaw to one of these feeds and went down in the middle of it, eventually you're going to find a little dipole antenna just like the whip antenna on your car. I mean, it's actually not so different in some sense. But we have ridged horns, which is this structure up here, and we cryogenically cool these things to make them more sensitive. So we make the systems very sensitive, but they're fundamentally 1 pixel and pretty much they observe at different frequencies, but it's 1 pixel. Now what was realized is that, the resolution that you got was proportional to the size of the dish, or inversely proportional. And people realized, well, what if I actually used an array of dishes? Rather than try and build a dish which is 1 kilometer across, which I can never really do, are there ways for me to actually use collections of antennas to do this? And in fact, there is a way. So aperture synthesis, which was the Nobel Prize in 1978, I think, 74 or 78. So what people realized was that by transitioning from single dishes to arrays of dishes, not only do you get the resolution associated with the separation of the arrays, but you also get the ability to instantaneously image the sky within some limitations. So, this is a huge leap forward. And of course, once that began, people kind of jumped onto it. So these days we build interferometers. Not always, there are still single dish applications, but largely radio astronomy is done with interferometers where we have a collection of smaller antennas sending signals back to a correlator. Correlator is, sort of processes the signals, actually does all the math required to generate the image. So even in the 50s, people started building simple interferometers. This is one of the earliest ones at Cambridge. At Owens Valley, people started doing it. And this is where the US kind of came back into the picture. After World War II, the US did not go into radio astronomy. It focused on optical astronomy. And it was really about 10 years later that it was realized that, in fact, they'd probably missed something. So in the early 50s, there was a concept of building a National Radio Astronomy Observatory. So National Science Foundation was formed, and after that, there was a sense of having a national observatory. So these days, we run these facilities. The Jansky VLA in New Mexico, which is an array of 27 antennas. We run the Very Long Baseline Array, which is 10 antennas distributed across the US, the Virgin Islands, and Hawaii. There's the Green Bank telescope I showed you earlier, and then there's the Atacama Large Millimeter and Submillimeter Array. So as I said, these 3 telescopes, they're all observing at frequencies, centimeter wavelengths, frequencies sort of like your cell phone, plus or minus factors of several. This telescope is observing at higher frequencies, and I'll tell you why in a moment. So I talked about Green Bank. As I said, the very common observation with Green Bank is looking for the radio emission coming from neutral hydrogen in our universe. The Jansky Very Large Array, this was a telescope started in the 60s, built through the 70s, commissioned in the early 80s. So the VLA is really the best radio telescope we have as a species. It's a remarkable instrument. It's on these 3 arms that you see here. It's in a Y configuration. And as I mentioned to you, the resolution depends on how far apart those antennas are. So you can kind of see the trail leading up here. It's actually a track, a rail track, and it goes out in the 3 directions. So we can have all of the antennas within 1 kilometer of each other, and then in the maximum configuration, the antennas are actually spread out along the 20 miles of track that heads off in each 3 directions. So in the maximum configuration, I think they're 35, the largest separation is 35 kilometers away. So the reason we do that is for resolution. When the antennas are close together, they can image a large region of sky at fairly low resolution. When the antennas are far apart, using the same algorithms and the same imaging approach, you can image a small region of sky at very high resolution. So depending on how far away in the universe your object of interest is, and how compact or large and fluffy it is, you might need a different configuration. So we move the antennas along this configuration. We have an 18-month cycle we kind of roll through. They're very far apart, and then they're close together, and so on. The other telescope I mentioned is ALMA, and I'll come back to ALMA a little later. In the same way, ALMA has a very compact configuration. It's always annoying the antennas are not pointing in the same direction. It's just kind of the way it goes. But on the largest configuration, we can space them out by about 16 kilometers. Here, they're probably 500 meters across or something like that.
Why then point in the same direction?
Well, so the theory is they're an interferometer. They should all be receiving the same signal. So if you take a picture of an interferometer, all the antennas should be pointing in the same direction. They just never are. Usually one antenna's not working, or someone's up in antenna 17 doing something. I think I have a few VLA pictures where over the course of 20 years you can get one where they're all working and pointing in the same direction. ALMA is more frustrating that way. Here's a different interferometer, and they are all pointing in the same direction, so I've been proven wrong immediately. This is a smaller array. This is the submm array up on Mauna Kea, but this is reconfigured. You see the different pads where the antennas are moved to get different spacings and to do a better job of the imaging. Now, this is where we're still using antennas as the receiving elements. You don't have to. There are arrays where, in fact, what we do is we put down series of dipoles. Essentially, we put down pieces of metal and we sample the radio signals that are landing in there. You add all of the signals up in one of these things, and then each of these is acting like a radio dish. This is a lower frequency approach. This is for frequencies which are perhaps a tenth or more of the signal of your cell phone. This is the long wavelength array in New Mexico. Again, these are actually the receiving elements. This is like the antennas in the array. And this is one in South Africa that is looking at even lower frequencies. You see the little receiving elements in here. And they're in these little buckets so they can't electrically see each other, actually, which is a problem. And this is a very regular array. You notice that most of the other ones are random because that produces the best imaging performance. This is very regular because you want to measure the same signal over and over again and calibrate it very accurately. And then I mentioned you can eventually get to the situation where the antennas are spread over long distances. In these situations, we don't necessarily try and bring the signals back in real time. What we do is we actually record the signals at the different locations. We put a timestamp down on the data stream. We bring all the disk pack backs, we whack them up on a drive, and then you press play, and it looks like all the signals are coming out of the ground, out of a set of fibers. And so this is very long baseline interferometry. It's more difficult, but it produces very high resolution. The resolution you get from something like the VLBA is about the ability to read a newspaper on the moon from here. That's the sort of sense of milliarc second scale resolution that you can get. Okay, so let's transition away from technology and start talking about physics. So what are the benefits of observing in the radio? So there are several. One is you can track physical processes which have no signature at other wavelengths, and as it turns out, the radio universe is kind of rich that way. Radio waves can travel through dusty regions. So when you're looking at radio signals, if you look at sort of background radio sources, you don't necessarily, you're not blocked by the galaxy. You can see right through the galaxy in many cases. It can provide information on magnetic field strength and orientation. You can do polarization observations. You can do line of sight velocities. And you can observe in the daytime, which is very civilized, actually. You can observe, when you've got a telescope, a radio telescope, you can observe all day, every day. It's very efficient. You can get a lot more observing time on the sky. Now, the kind of primary astrophysical processes, and this is just a small group, synchrotron radiation is a big one. I think we knew about synchrotron radiation before radio astronomy at some level, but the fact that when particles are accelerated in magnetic fields, they produce radio emission. And so when you look at our galaxy, it's threaded with magnetic fields. There are electrons which are being thrown into those magnetic fields from shocks and winds and other astrophysical events. They generate radio emission. And when we observe it, We can learn both about the magnetic field orientation, etc., but we also learn about the physical processes that accelerated the electrons. There is also thermal emission. So there's the black body emission that we all give off. So we don't have a strong sense of that. If I turned all the lights off in the room here and we really made the room dark, our eyes can't really detect the thermal emission from any of us. But if I heated you up to 5,000 degrees, you'd be glowing, and we'd be very aware of your thermal emission. And so it turns out that a lot of objects are giving off radio emission because of their thermal properties, and that was that calculation that Planck did so many years ago that suggested that we wouldn't detect that. Well, actually, we can detect that now pretty easily. It's just improvements in technology. So there's synchrotron radiation, thermal emission, and then there's really spectral line emission, which is this idea that atoms and molecules have allowed transitions and some unallowed. If you really know where to go looking in the spectrum, you can see radio emission from these transitions. And in particular, by looking at them and understanding the physics here on Earth, we can learn about the physical conditions in these distant objects. So this is what the sky looks like at radio wavelengths. If your eye was a radio telescope and you looked up at the night sky over Green Bank. And so it kind of looks the same, you might say. Maybe it doesn't look too different. But in fact, what you're looking at there is completely different to what your eye actually would see. So essentially, none of these are stars. They're all galaxies. They're all distant galaxies. And so, this is one of the big key results from radio astronomy very early on, is that when you look at all these point sources here, all these simple dots, they're all actually distant galaxies, much like our galaxy. Now, superimposed on that, you can kind of see these woofly things, this sort of shape. I hope you can see that. That's the plane of our galaxy. So as I said, as from the early observations, we understood there's radio emission from the plane of our galaxy. So what we see here is the plane of our galaxy, and then this point here is that radio emission at a very high distance. So we just see it as a point, for example. And then, there are so many galaxies in this picture. You're actually looking at lots of different types of galaxies. Some of them are much more exciting and active than others. I talked a bit about emission from warm bodies, the black body radiation. It turns out that for most celestial objects sort of floating around in the universe, temperatures which are much less than we have here on Earth, so 3 to 30 Kelvin are more common. And so the frequencies that we're looking at with like the VLA are not the best frequencies for that. They're sort of down on the Rayleigh-Jeans curve. You want to be looking at higher frequencies, which is what will lead me back to ALMA in a few minutes. And then there are other forms of emission too. There's free emission from ionized plasmas and so on. So, if you take those different types of radio emission mechanisms and you look across what's been done over the last 50 years, there are lots of key observations, and it started, I think, much more thinking about sort of radio-only objects, and these days it's much more integrated with sort of other types of observations and astronomy. So the cosmic microwave background, that was a Nobel Prize back in the 70s. Pulsars are largely radio-emitting objects. Quasars were sort of known optically, and it was actually through radio techniques that some of the breakthroughs were made. Gravitational lenses, we'll talk about. Energy dissipation from gravitational waves, I won't talk about until next week. Dark matter, masers, and extrasolar planets. So there's been a nice stream of Nobel Prizes really specifically in radio astronomy associated from these sorts of observations. But there is a gradient in here which I can spot, but it's hard to spot, which is that the earlier observations are much more about radio standalone, whereas the later observations are much more integrated into models of the universe and thinking about things like dark matter and so on. So, let's have some examples. So this was, remember that dot that I showed you up in that first radio observation? Well, this is it with the VLA. And this is a remnant of a star that exploded 300 years ago. And what you're really seeing here in the radio is radio emission from the ejector from that. So this gets a little bigger every year. And actually people recently have started to show that. You can actually see this thing getting bigger. So this is a VLA image at 1.4, 5, and 8.4 gigahertz, which provides some of the different colors. And really, when the star explodes, it throws out an enormous amount of material, electrons, protons, etc. And there is also the magnetic field that was both associated with the star. There's also sort of the galactic field which is around it. So when this ejector sort of heads out, it starts to sweep up that magnetic field. The electrons then interact with that magnetic field, and you get the radio emission. So this is a lovely image. It's kind of an archetypal image in some ways, and this will slowly get bigger. If we look at other regions of the galaxy here, so this one was not so far away, and it was not so long ago in time, so we can record this and we can understand this as an event. If we look at the plane of our galaxy and those woofly things that I was showing you in that image of the whole sky, they're exactly the same thing, except that those supernovae went off, tens of thousands of years ago or longer. This is a busy region, which is probably familiar to many of the people in the room here. So this is the center of our galaxy. You kind of see the plane of our galaxy running up and down here. Right down in the middle here is an object called Sagittarius A star, which is the black hole at the center of our galaxy. And this was also, that particular object was identified by radio observations. We can't see down into this very easily in the optical, not in the visible. In the near infrared we can do a little better. These days we can actually see stars and things down in this object, but the real detection of the physics and what's going on in here, you see this sort of, these sorts of structures here, the arches. This is a sort of magnetic field structure in the center of the galaxy. You see supernova remnants like Cas A that I showed you earlier. The other thing that we see in this region is lots and lots of star forming, and in fact Farhad is one of the world's leaders in studying the physics and the environment of the center of the galaxy here. So this is a 90 centimeter observation, so this is at 300 megahertz observing frequency. If you start to look at the VLA at higher and higher resolution, what you start to see are different structures. And so if take that area and blow it up, take that area and blow it up, you're really starting to get down now into the center of the galaxy, where there are winds, there are magnetic fields, there are stars forming, etc. There are masers which are radiating in spectral lines and so on. So that's one observation, and then you can blow that up even further, and eventually you get down here to this dot. And this dot is the black hole at the center of our galaxy. And I don't remember the actual mass of the black hole. What is it? 4 million solar masses. So orbiting this black hole, there are stars. And so I think you've had a talk from Andrea Ghez, who's talked about some of the infrared observations of stars orbiting Sagittarius A star. The other thing that we see in this region, there should be lots of pulsars. There are lots of stars being born, which means there should be lots of big stars which have died and become pulsars orbiting this region, but we don't see them. And I mentioned earlier today, this is one of the interesting problems in radio astronomy, is that we should be able to see hundreds or even thousands of pulsars close by and sort of orbiting this area, and we don't. Now there is a reason for that we think we understand, which is that this is way down in the center of our galaxy, so this is 24,000 light years away. And the first several light years and probably even further than that, there's a lot of ionized material. That ionized material disperses the pulsar signals. It makes it very difficult to detect them. We can detect them in other ways. We can do reasonably well with X-ray, for example. But so we don't see the radio observations of pulsars that we might expect in this region. So it would be really great if we could, because this is an extreme environment. This is this cosmic laboratory I talked about. Essentially the sort of the space-time effects in this region as these pulsars are sort of orbiting. It's what's called strong gravity. We can look for, we can do GR tests. We can think about testing different parts of gravitational theory and so on, except that we can't seem to detect the pulsars in there. So that's a challenge. There are instruments which are being built, like the ngVLA. I'll talk about it a bit later. I think I just killed my microphone. The ngVLA that I talked about a bit, I'll talk about later, that might be able to do those observations, but at the moment we've wasted a lot of telescope time on that. Another thing we can look at are extragalactic supernovae. So this is much like that Cas A observation in a distant galaxy. This is M81. This was a supernova that went off in M81. And what we actually see here is that over the course of time you see the supernova expand that way. And so, I think this is where we were 20 years ago, just making observations of these types of phenomenon. we're actually at the point now where people can think about things like jets coming out of these supernovae. People can actually start to do cosmology and really think about other types of physics associated with these sorts of events. So radio observations of supernovae has not moved very far forward when I think about it. Magnetic field orientation in galaxy. This is M51, the Whirlpool galaxy. So it's kind of a face-on spiral. There's kind of an interesting sort of sub-galaxy up here. As it turns out, these two components have very different ages, which I don't need to go into at this point. The thing that's sort of interesting about this is that we have some sense of how large these galaxies are based on our optical observations, and we have lots of great models for how galaxies evolve and so on. If you actually start to do things like look at the radio continuum, and then in particular look at the magnetic field orientation, you realize that it is possible to learn more about the formation of these galaxies with radio observations. You can see that the magnetic field lines are kind of threaded through the star-forming regions in this galaxy. And so while we have done a lot of this over the years, Farhad and I were concluding this morning that we had no idea whether or not these magnetic fields are actually generated by the galaxies or whether or not they're actually some primordial field that threads the universe, which are then swept up into these galaxies as they're formed. And so it's an active field of research. I mentioned to you neutral hydrogen in galaxies. We can look at the optical extents of galaxies and have some sense of where the stars are. If you actually look in the radio and you look at neutral hydrogen, what you realize is that galaxies are much bigger. And it was from some of the early radio observations that people realized essentially the dark matter problem, that there appears to be much more mass in galaxies than we can understand. Now, this hydrogen is not that dark matter. All this really tells you is that you can measure the size of the galaxy much further, but what it does do, these sorts of observations, is they very clearly show that the way that the stars are rotating out here at the edge of this disk, they are essentially rotating much faster than they should be, given what we see in terms of the mass of this galaxy, which implies that there's a lot more mass in here so to hold these guys in orbit. And the way that's typically resolved is that it's felt that coming out of the page here, sort of essentially spherically around this galaxy, there's a clump of dark matter. That there is somehow a sphere of dark matter around the galaxy. The galaxy is kind of in the midpoint, and it's the gravitational impact of that dark matter which is keeping these guys in orbit, even though there doesn't appear to be enough mass. So nice observation, and the radio was an important part of it. We talked about sort of special galaxies. I mentioned that there are galaxies in the universe that seem to be different to sort of galaxies like ours. There's a black hole in the center of our galaxy, and there may be a jet coming out of that black hole. But we can look at other galaxies and we can see very profoundly different types of behavior. So this galaxy, you look optically, you see a sort of a source there. If you looked at the spectra of that source, it would appear to be a little odd. When we actually look at it in the radio, you see that there are these two jets of emission that are coming out literally over hundreds of thousands of light years. And so there's really not much about this we actually understand, I would say. We do not really understand how these jets are produced and how they're collimated over these large distances. We maybe sort of understand how some of this radio emission is generated out here if you believe the jet exists. But it's very clear as we look through the universe, most of those little dots that I showed you on that diagram way back then, actually, if you get enough resolution, break up into this. This is what a lot of those galaxies look like. And so you can see the scale here is very large. It's 650,000 light years. So how does this happen? We think down in the center of the black hole here. So unlike our galaxy, where there's a black hole and it seems to be kind of in the middle and it's floating around and it has some stuff around it, there doesn't seem to be huge amounts of material pouring onto that black hole. But we very clearly see in the nearby universe even black holes where there's a lot of material orbiting. It's kind of like someone shoved a bucket full of stuff right at the black hole. As that material heads down into the black hole, it heats up from losing its gravitational energy. You get this large accretion disk, and then in some way we do not understand. It launches these jets. And these jets have some configuration. This is an artist's rendition. We actually don't know how it works, of kind of a spiral structure, and squirting out of this is a lot of material that eventually leads to those beams which go out for many hundreds of thousands of light years. So this is purely a radio phenomena. There is one or two optical examples, but largely this was discovered by radio astronomy. And we are now 30 or 40 years beyond this, and while we have some better ideas about how it happens, this is an unsolved problem. We do not really understand how this works, how these jets are launched, and how they're collimated over such long distances. And the problem is that they're everywhere. As I said, it's really very easy to look around in the local and the distant universe and find these properties where you see these jets squirting out, producing these lobes. This is a great one, etc., etc. So this is a major problem in radio astronomy. I think it's defeated one generation of theorists and it awaits the next. We talked a bit about the microwave background. One of the residual radio signals we see is the sort of the cool radiation that emerged from, it's the cooled radiation of the Big Bang. That's not what this is. This is sort of put in a projection where the galactic plane is running through the middle of the diagram here. And all of this stuff you see here is material in our galaxy. And so if you look, this is at 23 gigahertz. If you look at 33 gigahertz and you look at 41 gigahertz and you look at different frequencies, what you can do is you can actually start to make models for all this gunk in our galaxy, which includes us, and you can remove it. And when you do that, eventually you can remove it to the point. Oops, too far. Page up. You can remove it to the point. There's still some residual here. You can actually do better than this. This is 90 gigahertz. What you're looking at down here and up here at this point, this is the leftover imprint of the Big Bang. And so there's a lot of observing that goes on around the world looking at this radiation, because from this you can learn about gravity, you can learn about inflation, you can learn about the formation of structure in our universe. I might speed up a bit. Solar observations, the magnetic field structures on the sun generate a lot of radio emission. And again, this is not something we actually understand. We do not really understand how this high temperature emission is generated. This is another observation. I think Mark came and gave you a talk about Beasley, right? Yeah, by very accurately measuring the positions and the velocities of water mazes in our galaxy, we can delineate the arms of our galaxy, which is actually kind of hard to do. If you're sitting inside it, it's actually hard to see the other arms, through other arms and so on. But this is a lovely project which we've done on the VLBA over many years. This is the nanograv project. The goal here is to detect gravitational fluctuations from essentially binary supermassive black holes collapsing in on each other. When that happens, it produces a ripple in space-time which moves out. And if you're then looking at a set of pulsars through that ripple, you should see a particular signal. So these people have been working on this. They're here. I think they're actually down about here now and flattening out. So this is a radio way of trying to detect gravity waves. And I think they were hoping a couple of years ago that they would get the Nobel Prize for detecting gravity waves this way. Unfortunately, we detected gravity waves a different way. And so this is still an important project, but a little harder. This is a nice observation from the Very Large Array. When you look up in the night sky, essentially every other star you see is a binary star. Half the stars in the sky are binary. And so we actually don't easily know how to do that. If you actually look at the way that stars form, it's quite complex to think about how one disk and another disk would interact and how they would eventually collapse down into stars, because the reality is we don't really understand how this works. There are several key problems in that area. And so this is a nice observation that was done with the VLA and 40 milliarc second resolution. We can actually get to the point now where we can detect the disks in these binary stars. And this was a nice survey done by John Tobin and collaborators on the VLA over the last couple of years. And I'll skip that one. Okay, so I mentioned to you, how are we going for time? What's the time? I can't see the clock there. 15 minutes. Okay, good. I mentioned to you that most of the observations I was talking about, and a lot of this, for example, all of the radio jet phenomenon, this all happens at centimeter wavelengths. This is all frequencies like your cell phone and TV and so on. I did mention that thermal emission, it's possible to observe it, but you need to go to higher frequencies. You need to go to frequencies which are 100 or 1,000 times the frequency, sort of 100 gigahertz to 1,000 gigahertz, terahertz. Now at those frequencies, water vapor in the atmosphere absorbs and distorts the radio signals as they come down from space. And that's not true lower on. You can observe during the rain at lower frequencies. So if you do want to observe at those frequencies, you've got to go to very high dry places. And this was realized for many years. There were some millimeter arrays that were actually built. But over the last 15 years, the US, working with Europe and Japan, built ALMA. So these are the Andes. And this site here is at 16,500 feet. And so this is about as high and as dry as you can get within practical limits. And it was at this site over the last 15 years that we built ALMA. And so ALMA is an array. It's similar to the VLA in many ways. We move the antennas around with this kind of funky transporter where the people are sitting underneath here. It's kind of a horseshoe that backs onto the antenna, lifts it up. We move the antenna to a new place, and then we put the antenna back down. It sounds like fun, but it's actually not much fun. These are the antennas. The antennas kind of look like the other antennas. You have a subreflector and then a receiving element in the back here. Underneath the dish there, you have this cryostat here where all the receivers are. If you looked inside there, you would see these are all the different ALMA receivers and so on. So ALMA was, these countries making a major commitment to building a millimeter array. And so this is, coming up to nearly $2 billion worth of investment over the last 20 years, I think you would say. This is the high site very early on where you have sort of the observing building, and this is when some of the earlier antennas are up there. This is kind of a cool drone video. That's the building. Then you're flying around. Here's the transporter moving an antenna. You see the antennas distributed here. There's a volcano down there. And then you see all the different antennas up here. And we have different multiple sizes of antennas for a reason I don't need to go into. So ALMA is sort of the state of the art in terms of radio interferometry. And as I said, it's observing at frequencies which are much higher. So, like any project, you have some idea of what's going to come out of it. I think it's fair to say that ALMA has probably vastly exceeded what we imagined. So this was one of the great results from ALMA. This is looking at a star called HL Tau, which is about 450 light years away. The scale you're looking at here is much bigger than our solar system. In fact, most of our solar system up to about Uranus would fit within this central yellow dot. But what you see is going out from there, this is dust emission, and you see these rings. So these rings are indicating the presence of planets that are forming. So inside each one of these rings is an object which is essentially scooping up all the material as it accretes the material going around, which is the modern definition of a planet. But what you see here is that these objects are at much greater distances typically. This whole thing is 5 times the diameter of our solar system out to Pluto or something like that. So it's much, much larger. So what we really started to see for the first time is how are planets forming around stars, although we don't see down on terrestrial scales. And I'll come back to that. It's an important point. Another amazing result from ALMA was that we realized that much like those dots I showed you in the sky above Green Bank, if you look at millimeter wavelengths, there were these very bright sources. You could do that with single dish telescopes. If you actually looked at them with the interferometer, you could resolve them into rings. And what they are gravitational lenses. In the foreground here, there is a galaxy. In the background here is a galaxy that has some radio emission at the frequencies we're interested in. And as the light from that distant galaxy comes past the foreground galaxy, it's bent into our field of view. And so if that happens symmetrically around the galaxy, you would get a ring. So when you make observations like this, there's just like a lot you learn, right? You learn about the mass of this galaxy here. You learn about the mass distribution inside this galaxy here. You'll learn about the physical properties of this galaxy, which interestingly you might not be able to see regularly because it's too dim, it's too far away. So the amplification you get from the gravitational lens is telling you about information about galaxies that you wouldn't normally see. You can also measure spectral lines in these galaxies, and you can learn about the evolution of metals in them. So this was an amazing result. So this is just 2 examples of the science that ALMA is doing. There's only several thousand of them on the web that you could Google up and find. So ALMA at these higher frequencies is really exploring kind of the thermal universe. It's looking at the radio emission that's coming from thermal sources. Okay, so let's just turn back slightly to the VLA. The VLA was sort of built in the 70s. In 2011, we did one major upgrade of it. So the VLA is really a remarkable instrument, and this upgrade that we finished several years ago has greatly improved its properties. But in particular, emerging from that observation of HL tau, this idea that we really had an opportunity to get down now and start to look at the disks around stars, we've been talking about what we're calling for the moment ngVLA, a next generation very large array. And so it's a different talk, and I'm not going to necessarily go through all the details here, but the goal is essentially to increase the size of the VLA by a factor of 10. Increase the collecting area and actually increase the linear size of the array. Now there's several reasons to do this. Science reasons as well as technical reasons. So maybe I'll move on. This is kind of a simple simulation. This is the current VLA here, looking like a fidget spinner. And you see sort of the places where we're considering putting other dishes out into Texas, into northern Mexico and Arizona and so on. So I'll show the glitzy video. Is it moving? Yep. So we'd be going from 27 antennas, which are 25 meters in diameter, to 214 antennas, which are 18 meters in diameter. So that's a kind of a major upgrade. And in particular, the focus is on higher frequencies, and I'll show you why in just a minute. So this is kind of one of those things where you show these very sexy, smooth pictures of the antennas, and then you kind of pull back and you start to look at the antennas in the center of the array, and there's a lot of antennas in the center of the array. And it's the goal here. There's a particular science case for that one. Then you pull out and you see the current size of the VLA, and then we start to place more antennas around it, and you continue to pull back. And it's by placing those antennas out there, you're getting the angular resolution you need to do the science case I'm about to show you. And you hit the state border, and then you keep going and down into northern Mexico and out. So by the time you finish, the actual linear extent of the array, rather than being 35 kilometers, is more like 500 kilometers. And so this is a factor of 10 in linear resolution and a factor of 100 in angular. And then eventually we could link the VLBA antennas into it as well. So what are the science goals for doing this? What's the real underlying thing? So these are the 5 key science goals. One is unveiling the formation of solar system analogs, probing the initial conditions for planetary systems with astrochemistry, looking at the structure and evolution of galaxies, detecting those pulsars in the galactic center that I mentioned to you earlier that we seem to be having trouble with. And then there's just generally the science of those radio jets, supermassive black holes, and how they exist in the universe. So this is a sort of a simple video that quickly goes through and kind of talks about that HL tau image. As I mentioned to you, you've kind of got these rings in here, which give you some sense of, created by Saturn mass planets is the model at this point. 1 AU is the distance from the Earth to the Sun, so this is much bigger. But we can't get down into this area. So what we did do after the HL tau observation was made was to see what we could do with the very large array. And what you realize is that you can actually get down, is it added? Right. You can get down, and what we started to see when we added the VLA data is this region in here starts to get clumpy. So you're starting to get down to terrestrial planetary formation scales here. This is the area where we can start to see planets like Jupiter and the Earth and Mars and so on forming, but we still don't quite have the resolution. So by building ngVLA, by increasing the linear size of the array and the collecting area, we can actually get down to these sorts of scales, where it should be possible to actually see some of these planets forming. And the other key issue is that at this level, we can actually do chemistry. We can actually look at the existence of organic molecules on these scales. And this video gets a little silly at the end because we eventually zoom in, and by that point you're so close you can see people waving on the planet, and it all gets a little silly, like that. There we go. Well, those are the molecules. So these are the simulations of what it would look like, 5 AU being kind of Jupiter distance. And what you can actually do, these are the simulated observations. ALMA can't do this. ALMA is not big enough, and it turns out that if you go to higher frequencies, you have issues. But this is really, this is the state of the art. It should be possible if we built ngVLA to make this observation. We could actually see planets forming and rotating around nearby stars. And simultaneously, we could measure the chemistry of this. And so obviously, if you look at the chemistry of this kind of object and you don't detect any organic molecules, you can draw some conclusions about whether life is possible on that. If you detected certain types of organic molecules, if you detected water, for example, you might come to a different set of conclusions. And that's one of the observations, it's one of the advantages of radio, is that we can do, if you look at any section of spectrum, there's emission from all these different molecules, and with the ngVLA we have the sensitivity to actually detect thousands and thousands of these organic molecules. And so you'll be able to draw conclusions about what the prebiotic state of some of these systems are. I mentioned the other one, which is charting the evolution of galaxies. ALMA is doing some of this work, but what we really see is you've got to do kind of the low order carbon monoxide transitions, which is not something you can do with ALMA. So there are sort of amazing opportunities to look at the first generations of stars at the very high redshift, very early on in the universe. And there's a broad science case which has been put together. So just to finish up now, the big news we had is that a couple of weeks ago we actually acquired $11 million of money from the NSF to look into the design development of ngVLA. We're expecting kind of a 7-year development cycle for that. So it's really good news. We visited Mexico a couple of weeks ago to talk with them about putting the antennas in northern Mexico. Putting stuff on the border is kind of exciting right now. So putting good things on the border is a good thing to do at all times. And so this project is kind of moving forward. What typically happens in our community is that the science will be evaluated, kind of the technical definition of the project will be evaluated, and then it will compete in the marketplace in the decadal survey, which astronomy holds in this country every 10 years, and it will compete against other projects at optical and other wavelengths. So that's it. So radio astronomy, there's a long history of success in many areas. I'm proud to say that NRAO is a global leader in the field, and we really do have the 4 best instruments in the field, and I have not managed to screw that up over the last 5 years. The field is growing rapidly. ALMA and ngVLA, I didn't talk about the square kilometre array, which is a global project which is underway. All of these instruments, while they continue to make observations and discoveries which are very radio oriented and very radio specific, very much astronomy is a multi-wavelength game these days. Is that ALMA provides information which is combined with other sorts of observatories to really generate the understanding that's needed to move forward. Scientifically and technologically, really the frontier awaits. There are some key problems for ngVLA which need to be solved, but very much human capital is important. There are sort of many situations we encounter now where it's having the people that are trained and interested in the science and capable of using their hands and their head successfully to solve the problems of the observatory. They are in short supply, so I strongly recommend you think about that as you move forward. And just finish by saying, the National Radio Astronomy Observatory, we seem to be doing okay. We are your observatory, and we look forward to your proposals. So thank you. Questions?
Yeah, you mentioned that to go to the 1 AU threshold and below, you need the ngVLA, but of course ALMA is also exploring the possibility of longer baselines.
Yeah.
And you had mentioned some problems with going to the highest frequencies, or issues you call them. I wonder if you could elaborate on that.
So do I have a map? I don't have a map. So the issue with ALMA is that you're on the Andes, and so while you can probably double the resolution of ALMA in a reasonable way, you're not going to get 10 times the resolution, because to do that you're either in Bolivia or you're down at much lower altitude, and you're not going to be able to do the same kind of science. And so that's kind of the problem. The other problem is it's massively expensive. That a VLA dish, the ngVLA dishes we're talking about, I kind of want to pay like $1 million per dish for those or something like that. An ALMA dish fully loaded is like $8 million. And so it's difficult to do that. So that's kind of the cheapness problem. We're cheap. The other problem is that the terrestrial regions in these objects are optically thick at high frequencies. So you actually can't do the observation on ALMA, right? If you go up to a few hundred gigahertz, all of that dust is optically thick, and so you can't do the observation. So that was sort of the remarkable result that came out of ALMA, is that actually something between SKA and ALMA that had enough resolution and collecting area could actually get through that to do those observations. Yeah.
So I gathered from that answer that the reason for the next generation VLA site choice was so that you could have the baselines. But looking at you want to get up to 116 gigahertz, how much time do you think you can observe at 116 gigahertz given the weather conditions?
So the VLA site's at 7,200 feet. So it's actually a great 3mm site. Yeah. It's true that by the time you go out to the longer baselines, then you're at lower altitude, and so you've got less opportunity. It actually turns out that the sweet spot for those protoplanetary, I think the simulations I showed you are like 40 gigahertz or something like that. So you can do 40 gigahertz down at much lower elevation on longer scales. So yeah, if it's raining, you're screwed. But in general, if you look at 3mm, most of that's being done at the VLA site, and the VLA site's actually a very good 3mm site. And at mid-frequencies like 40 gigahertz and so on, you'll have lots of time where you're getting all of those ngVLA antennas effectively. Yeah.
Do you have a question?
It was a silly comment. CERN straddles the border between Switzerland and France.
Yeah.
So I would put it right across the wall.
Well, I will say we were down there a couple of weeks. We were actually down there when the earthquake happened. I will say that our Mexican colleagues down there, they are very interested in this as a form of science diplomacy. There was kind of a lovely phrase which they used, which was, this was a different border in some ways. And so, yeah, all of these arguments help along the way, sure. Yeah.
So are there sources of funding other than the NSF? Because it sounds like 11 million will not be enough.
Well, so, typically the way it goes, if you build a big telescope or a big facility, particle physics facility, you might spend 10 to 15% of that, of the capital cost of the project in your design development phase, right? So if the price tag for ngVLA is probably about 1.5 billion, plus or minus. So that would argue that we're going to spend $100 million in design development. That's not what we're aiming at. At this point, we're aiming at about 50. So I've got the first 11 of 50, and I have 2 or 3 years now to generate another 39 or something like that. But we'll have partners that will come along, and that's kind of the way the game is played. Beyond that, then yes, you need to find the major sources of funding. We're kind of imagining that the US would be 2/3 of the project, and that foreign partners would be another third. So the ask potentially for the US is $1 billion. So we've spent money like that on ALMA and other things. It's not easy, but not impossible. But there is an interesting thing. There's a kind of a very profound difference between radio and optical in this country. So optical astronomy has a lot of private money going into it. I'm a billionaire. I want something on a mountain that has my name on it. I can do that, right? Radio facilities are much larger. They usually involve a lot more federal money. And so there's this interesting, unfortunate fact, which is I'm a billionaire. I like your radio project. The government's putting $1 billion into it. I can put $15 million into it. How am I getting anything out of that in some ways? So there really isn't a lot of private money or philanthropic money that goes into radio astronomy. It is large scale and largely federally funded. But it's hopeful. We certainly wouldn't say no. But actually, nearly all radio telescopes, all major radio telescopes built in the last, not all, but nearly all in the last quarter century, I think, are all federally funded primarily by some government. Yeah. One more? Yep.
So are you working with the SKA, competing? I mean, you just said that you're looking at foreign money as well.
Well, I am so glad you asked me that question. So, as it turns out, I mean, one of the issues that we have, F5, is that yeah, you do have to be able to define yourself in where you are with respect to other projects. So it is kind of the case that if we look at SKA, this is the slow, stupid way of doing it. You know, SKA is not able to do this kind of science. Shift F5, and one more, and one more. So if you look at frequency versus effective collecting area, this is where you kind of find ALMA now. This is where the current VLA is. This is where SKA is thinking about dominating, and this is where ngVLA would dominate, right? And so really, this is this does a poor job of representing ALMA's capabilities, because in fact ALMA is absolutely stunning at higher frequencies than this. It does a poor job of showing what SKA is capable of, because SKA's contribution down below a gigahertz is just stunning and much larger. So the whole goal of ngVLA is to kind of fill the gap between the two of them. So there are technology overlaps, there are problems that we have that they also have. So are we competing with them, or are we collaborating with them? Yeah, at different times, yes. And that's healthy. I think that we have found solutions. We have software they need. They may develop some technologies and antennas that we would use. It's healthy rivalry, I would say.
I have a question.
Yeah.
So you never really mentioned about history of space-based radio observatories. And it looks like NRAO really never got into space-based. What's the future in that direction?
Sure. Maybe I can explain the history, which is that most space-based research in the US is NASA funded, and NRAO has been primarily NSF funded. So that's not a reason, but it follows the line in some ways. There are projects, there are low-frequency radio astronomy projects which are being planned to do things like epoch reionization and so on, and we are part of those. I showed you those CMB diagrams earlier. NRAO produced the amplifiers that flew on WMAP to produce those results. So we've done a little bit of it, but you're right, it has not primarily been a thrust. We've thought about it. The issue, one of the issues it generates is kind of a security issue, is that as a ground-based radio astronomy effort, federally funded and so on, we don't run afoul of ITAR or anything like that. Whereas if we were to get involved in space projects, it would require us to do a major overhaul of the way that we operate and the way that we run our facilities and so on. And it's just more money and doesn't necessarily seem like the way to go. So there are space radio astronomy options. We are connected to some of them in major ways. We've never really adopted it as a major strategic point. In fact, I think we had an opportunity to do that a couple of years ago, and we sort of explicitly decided that dealing with the ground was sort of the way to go. But there are opportunities, for sure.
Okay, great. Well, thank you so much.
Thank
Let's
you.
thank the speaker again.